Hi, everybody. This is Bert. I'm trying to start the recording. I think it is recording now. Good afternoon, and welcome to the continuation of our class. If you can hear me, just maybe somebody can say yes in the chat, so I know that at least. Okay, good. Yeah, so I wish everybody, of course, a very happy New Year. Best wishes for the new year. I hope it's going to be better than the past year. Today's class is on dynamic models. Dynamic models by itself is a very big topic. You can take a full class on dynamic models for control in our department, on video processing, which is all about dynamic models for processing video signals, of course, also in signal processing. So these are really big topics. But what I wanted to do in this class is to keep it deliberately a small chapter, because I kind of want to show that while it's a big topic, on the other hand, there's nothing new about it if you take it from the perspective that we've been teaching, this Bayesian perspective. The only thing that is different is that now every observation is not independent of every other observation, right? So if I am going to share my screen, let's see if I can do that. Yeah, so the only thing really is that we cannot use this assumption here, that P of T subscript T, which is short here for the whole sequence x1 through x capital T, it's not just the multiplication of the probabilities of the individual observations, right? We can still decompose it, but there's going to be generally, it's an ordered sequence, right? So there's going to be some dependency of basically of an observation from the past. And then, but aside from that, it is a matter again of just setting up a model, a model proposal, and defining your inference problem. Okay, so okay, so a lot of people have audio problems. Okay. Then I'm going to switch the audio to another device. Okay, so now I'm actually switching to the to a remote, well, basically to the microphone on my webcam, which I hope is better. Is it a little better? Okay, super. Then we're going to do that. Yeah, so I was saying that while it's a big topic by itself, dynamic systems, on the other hand, it falls within the same structure of what we've been doing. You make just a proposal for a model, a probabilistic model, and if you have any task, whether it is updating states or making predictions or classifying signals, learning parameters, you try to phrase it as an inference problem, and then, well, if everything is Gaussian, you can basically do that inference problem analytically. And if it's not Gaussian, well, then we can go to all the methods that we've looked at. That includes Laplace transformations, message passing in graphs, variational Bayes, and there's other methods, Monte Carlo sampling. So that's basically all there is to say. I'll give then an example of in this class of basically an inference problem that is very common, and that is the Kalman filter, which is if you have a state space model defined by these two equations, and a state space model can also be visualized by this graph here. This is a vector graph. Then the idea is that you want to estimate the hidden state z of t from all the past observations. And since everything is Gaussian, you can work this out analytically, and I do that. I do that here. It's quite, as you can see,
quite a derivation. It's not a derivation you're going to be asked to do in the exam, but the point is that it's possible, and it's still a lot shorter than you would find if you go to a regular, let's say, control systems book, and they probably spend 3, 4, 5 pages on deriving the Kalman filter. So interestingly, you can also compute the evidence, so that makes the derivation even longer. It's in the optional slide, but since everything is Gaussian, you can always compute everything here. This is just an example. On the other hand, Kalman filtering is very important in control and also in signal processing. So it's good to see what's involved in doing Kalman filtering. And that's basically the class. There's multidimensional versions of Kalman filtering. All of this stuff would also work if, let's say, if it's not Gaussian, but then you can't do it analytically. And so the whole literature is about how to do inference when things are not Gaussian. And so in our lab, we use message passing. And in other labs, they may focus on Monte Carlo sampling or on other methods. And yeah, that's what let's say the probabilistic machine learning world is about at the moment. So with that, I'm going to give it up to you again to ask questions if you have any. The main thing, just to summarize this, is not for you to understand everything about dynamical systems, but just to understand that it really fits within our framework. And a lot of algorithms that are derived in all kinds of ways in other books can also be derived by just applying the rules of probability theory to a given model. So if you have any questions, either open up your microphone or write something in the chat.
I have a question.
Yeah, go ahead.
It's a bit of a general question as well. But to what extent do we need to be able to really apply this material? Because in the questions, it's more about knowledge and do you understand the different types and do you understand the equations? But for example, with the example that's at the bottom of this notebook, it is really applied into Julia. To what extent do we need for the exam to be able to really apply the material?
Yeah, not to a large extent. So the exam is going to be multiple choice. If there are, let's say, calculating questions, then you're going to have to pick from 4 or 5 answers. What is the right answer? There may be a question, or we may give you, like, let's say, a piece of code like this and just take out, let's say, these 2 equations and ask you to fill in these 2 equations. But even then, it will probably be multiple choice, like pick the best 2 equations that will complete this Kalman filtering example. Really going to an application, applying Kalman filters to applications is, of course, what we want to do. Unfortunately, in this class, we don't have, we don't have the time, or have to make the class even bigger. So that you can do if you want to do an internship. In this class, I want to give a broad perspective over the different methods. It is a bit on the overview side. We do some coding and we do some exercises, but we don't really get to a real application. That's true. And also in the exam, I will not make it much different from what you're used to in the class. Does that kind of answer your question?
Yeah, thank you. So maybe a follow-up question then would be, do you also offer any courses further this year in which this theory is actually applied, or is it just internships or different courses?
There is a follow-up course, or follow-up. It's going to be taught in the 3rd quarter. It's called Software Engineering for AI Systems. Something like that, 5ARA0. That goes a lot into real programming. It's all about programming for AI systems. And so I think there will be much more opportunity to actually work on applications with these kinds of things, but also deep neural nets. So it's not limited to probabilistic machine learning, but it's more general on AI systems, machine learning. These types of models that we do in this class will be, you're also going to be able to work with those, with our models, let's say, but also with deep learning. And the focus of the class is to teach you how to do, let's say, how to improve your programming skills. Also, not just programming a little piece of code, but how to work with Git. So it's you do some version control and maybe some things about good programming style, how to name your variables and that kind of thing. But so there's an opportunity. And then, of course, internships. Yeah, I would say lots of problems actually also in industry, in interns in industry, can be phrased as Kalman filtering or Kalman filtering problems. Amazingly, how many problems can be phrased as a Kalman filter. Let's say in a general sense of having a dynamic system and then do some Bayesian filtering in that system. Yeah, that's it. I would go to that class, or you can go, of course, to this, let's say, the really specific classes on control theory or video processing. There you also get more chances, I think.
Okay, clear. Thank you.
This is a bit of a fundamental class, right? Sort of a basic class, with the idea that you can apply this to video processing, signal processing, control. Yeah. But I think the 5ARA0, so the AI for software engineering, software engineering for AI would be a good follow-up.
Yeah, thank you.
And just to say something about the exam, I think we already talked about it last time. There hasn't been really any changes, but just sort of, it's going to be a multiple choice. As far as I know, the decision on whether there's an option to actually make it on campus, as far as I know, that decision hasn't been made yet, but it looks unlikely to me. So either way, whether you opted to do it at home with so like an online test or on campus, in both instances, I would prepare with the ANS Delft system, so the online. I would prepare for the online session, because if on campus gets cancelled, let's say 2 days before the exam, and that's possible, then you have to do it online. If you do not want to make it online and there's no option to do it on campus, then your next opportunity is the next exam session, right? So I think everybody should at least prepare that it's going to be online, and hopefully you can go to campus if you signed up for that. Okay. Any other questions? Is there a wrong answer correction? I'm not sure yet, because I'm in the middle of making the exam. The exam isn't ready. I tend to not want to do that because it may discourage people. Every time you make an answer, you do an answer, and it's wrong. You think, shit, it's wrong. I'm not going to make it. So I tend to not give online immediately. It's wrong. It's wrong. It's wrong. So unless everybody in the class wants to get this immediate feedback, I do not give. You will not get immediately the grade, even though it's multiple choice. So in principle, it can be corrected a la minute, in the same minute. But the reason why you don't get the grade immediately is because I want to potentially scale a bit. Let's say if it might be that nobody gets my questions right, and then I need to scale you up. Or if everybody gets everything right, I need to scale it down a bit. And I need to take care of this of the people who score between 4.5 and 5.5. I might upgrade them to a 6, as we talked about. So that's why there will not be an immediate grade. Yeah, but definitely within the deadline, of course.
Yeah. I meant actually something else. So if you have a wrong answer, it's the guess correction, I believe it's called. Then you get, for example, minus 0.1 on your end score. Is something like that implemented, or is it just if you have a wrong answer, you have 0 points?
Yeah, I mean, I also am not sure. I will definitely will let you know before the exam. I've seen that option is there in Ans. I'm making the exam in this system called Ans Delft, and I see when I actually make a multiple choice question, I can of course give, let's say, a point to the right answer, and then I can choose if you do a wrong answer whether I want to subtract 1 point or half a point or 0. And what are your opinions about that?
I feel it would discourage giving answers when you are not 100% certain. So if you are if you think you have the right answer but are not sure, you have to think about whether you want to take that risk or not. And me personally, that I would feel stressed out by that.
You feel more stressed if there are negative points.
Yeah. Because then I have to make the choice of, will I take the risk to give an answer that I'm not 100% confident in? And for me personally, that would be stress.
Okay. Because if there are negative points, you may actually consider skipping a question if you're not sure.
Exactly.
Right? Yeah. So I think that's, I mean, if we can do a poll, and if the majority agrees with this, then I'm not going to do it. I don't want to give you any extra stress. There's already enough stress. So, so are there any other people who want to say something about this?
Well, I think most people would agree with what's said so far, that the penalty for a wrong answer will eventually always make the afweging.
Yeah.
Sorry.
Trade-off.
Yeah, the trade-off of, am I going to answer this question or not? For me, most of the time, it's a waste of time during the exam, because then I'm thinking about whether or not I'm going to answer a question instead of just going through the actual questions.
Okay, so I'm not going to do it then. I mean, I have no intention of adding stress upon you beyond having the exam already. So it's agreed then. I will not subtract. The result will be that almost all of you will get a higher score, right? Because there is then always a chance that you just guess. You will always have an answer, and you will guess. And so let's say even by guessing, you will get 2.5 points. But I will take care of that in scaling. I'm just going to wait for what all the answers are, and I'm going to want that a really large percentage of you just pass the class, and so I'll look at the distribution first. But I will definitely then not.
Is that also a machine learning application from the data of the student knowing it and the probability of just guessing that answer right? How likely is it that the student actually knows their stuff?
Yeah, I don't know. I mean, if there are 100 questions, and every question has 4 answers, and you would just answer randomly, you'll probably get about 25 correct answers, right? when even if you know nothing about the class, so there is sort of like, so everybody I think will get at least 25 good answers, and that leaves less room for you to differentiate yourself from others. Like I said, I mean, I'm in the process of making the exam, and I saw that option, and I was thinking about it, whether I should do it, but you convinced me. I will not subtract points. I haven't really thought about very much about how I'm going to determine the final grade. I think there's a large enough group, let's say that 100 people take the exam. That's large enough that sort of scaling everybody such that, I don't know, what is normal, 75, 80% will pass the class. That may be a good idea, but I'll have to see the distribution after I see all the scores. But what I don't want is that, let's say, 50% or so passes the class, right? Then I'm going to scale everybody up. But if everybody scores very highly, well, then we'll see what we'll do. But I'll try to keep it as fair as possible. And so I will not do any negative scoring. Any other questions?
Yeah, I had one question at the very top at the AR model. There you have sigma squared, and at the video lecture you mentioned that there should be a subscript k. Is that indeed the case? There should be a subscript k or not? Or is it one sigma for all distributions?
I mentioned that for here, this sigma squared.
Yeah, this one indeed.
Okay, yeah, not a sigma k, but rather, I mean, the most general case would be a sigma sub t, right? You can imagine if you would write this out, this just said that x of t is a1 times xt minus 1 plus a2 times xt minus 2 and so forth, plus a bit of noise. And then you have to make the decision whether that noise term has a fixed variance, which I do here, or a time varying variance. So the k is limited really to this sum here, but most general case would be, let's say, sigma sub t. Do you see that? So if I said k there, then that's definitely wrong.
I also have a question about the Markov condition.
Yeah.
Is that like a general rule? Is it always true, or is it more of an assumption? So it says, if I translate it into words, the probability of the state C of t given C the entire all C's up until t minus 1 equals probability of Z of t given the Z of t minus 1, because I'm a bit confused also with the subscripts and the you have the powers.
Yeah,
sometimes
okay.
you have t on top, sometimes at the bottom.
I see that it's not. I see that can cause for some confusion. Yeah, in this class, I mean, I'm not sure if it's good or in this lecture, I decided to move. If it's a superscript, that means 1, 2, t minus 1. Maybe I should change that notation. But this idea, right? The probability z of t given all the entire path. You can imagine if t just goes on and on and on, the string of observations that you need to depend on just becomes almost infinity, right? So that's not, you don't want a model that just grows in size every time when you get a new observation. You kind of want to have a model that is limited in size, right? So you need to stop somewhere. And so if you say P of Z only depends on the last sample, so everything that happened in the past, that's relevant for predicting the future, I'm going to store in the vector Z of t minus 1. Right? That's really the idea, that everything that is relevant for predicting the future, I want to keep, and everything that is not relevant for predicting the future, it doesn't have to be represented in Z. If you just do that, this is called a first order Markov condition. And you can do some theorems about that. You can, for instance, prove that with this theorem that the future is independent of the past given the present state. Right? The prediction for future x of t given z of t is independent of what happened in the past. Z of t determines your memory, basically. There's other theorems you can prove around that. It's called first order because if I would say no, z of t is depends on z of t minus 1 and z of t minus 2, okay, then it's called the second order Markov condition. So the Markov condition just, let's say, limits the past to a certain cutoff point, and then how many terms is the order. And then, yeah, it's actually, I mean, there's a whole, yeah, like I said, a whole bunch of theorems around that. But the thing that you want to remember about this is it fixes the size basically of your model. And the other thing is that if you do this, then, and this is the exercises, you can kind of show that whatever you want to predict about the future, it has to be represented in z of t. You cannot use, let's say, because the future is independent of the past given all your state variables. That's sort of the idea of this model. You kind of can see that also in this visualization, in this graph, right? If I start passing messages, let's say I want to compute here, let's say here an outgoing message. So then here I get my observation. I can actually go down. So here message 7 comes from my observation. Message 5 summarizes everything from the past. Right, there's no whatever x1 was, or in the past, or the prior, or whatever this distribution was. Well, it's all incorporated in message 5, and that's all you know about the past. So in message passing, it's kind of obvious.
All right, thanks.
So the question is, can such a state space model then also forget things that it has seen before? And is it more difficult for the model to remember things from longer ago? Yeah, absolutely. So a state space model can definitely forget things that that in retrospect you would have liked to know in order to predict the future. The thing is, of course, you don't know the future unless it's there, so you don't know what you need to remember. So there's always, no matter what you do, there's going to be a risk that you don't, let's say, remember the right things. There is in the machine learning literature, there is this sort of device or say model called the long short-term memory, the LSTM. And that's sort of a system that tries to remember things from long distances, right? But generally, that is certainly a problem with state space models. So you want to make them flexible enough that you can sort of learn what you need to remember. Any other questions? There are, by the way, models or other approaches to, let's say, to battle that problem of forgetting things that happened long term in the past. I mean, generally, it's a good idea to kind of pay a little bit more attention to the recent, let's say, to the recent past than to things that happened a long time ago, right? There's generally more correlation between, let's say, what happened recently and the future than things that happened a really long time ago. So, I mean, the general thing is of a state space model is really good. But if you have a fixed factor z, and you keep going, I mean that the size of that factor, if it cannot grow, then you're going to have to replace at some point existing information with new information. So you're going to have to forget, unless you grow your memory. But that's and so there are models that grow in memory. But then the problem is how do you going to keep growing and then until your computer just breaks? I mean, so there is just the challenge is to build models that capture, let's say, the relevant information that you need in order to predict the future. And the better the model proposal, the better the job you will, the better the job it will be at that task. And so that is the search, right? Try to look for models that have the maximum Bayesian evidence for the data set. Any more questions?
I did have a question, and it's actually about the vector graph under smoothing, so where we're at right now.
Yeah.
Basically, if you use this, you use information that you only have in the future. But is this like a backwards update? So you had your forward method processing, which got you to mu x2, z2. I can't really read it. And then if you go backwards, then afterwards you go backwards, or how does this work? You already did the observations.
Right. But I mean, just let's say the literature mentions on state space models mentions three classic tasks. One they call filtering. Filtering is this task: estimating ZT given x1 to t. So given all observations until this time, what is the current state? They call that filtering. Then the literature says, now let's make an estimate of z of, let's say, t, given x1 to capital T may lie in the future. So as you can see, if I want to estimate here z2, I'm not just using observations x1, but also observation x2 all the way to x10. And that may give you more information about what z2 is. If I have a time series and I want to project, let's say, the next point, I can do that. But if I have a time series and I actually know the future after the next point, but not the next point, so I have a time series that I just cut out one point, it's much easier, right? Because you can also, let's say, predict backwards from the future to that point. And that's what happens in smoothing, right? In a certain way, machine learning, just learning parameters, is smoothing, because you've collected all your data, and let's say the parameter is not really stuck to any point in time. well, maybe smoothing isn't the right word for parameter estimation. Parameter estimation would be a parameter that is not a function of t, and z here is a function of t. But smoothing, yeah, very often it still has many applications in communications and also in control. Sometimes you have a system where you really need to know, let's say, in this graph, this value after you have collected a set of data. Prediction, yeah, prediction is predicting the next observation or future observations given a data set from the past. Note that in the graph, I've not colored this now with a, not colored here this small black dot because it's not yet observed. Here it is observed. These are observed. This one is not yet observed. So I need to compute this outgoing message here. Yeah. And yeah, that's what we call prediction. The thing I wanted to show is that these three different inference problems have representations or visualizations in message passing.
Okay, but if I understand correctly, because the other two were clear to me, but for smoothing, it's basically updating your parameter estimation with the new information at point C2 with the new information you had.
Yeah.
From the later.
Yeah, let's say, sure, from observations that if I just give you this, let's say this model, and I tell you, okay, with this model, I've collected 10 data points. And now I need you to compute posteriors for Z1, Z2 to Z9 or Z10. Then what you will not do is say, okay, in order to estimate the posterior over Z1, I'm just going to use the prior. In order to estimate the posterior for Z2, I'm just going to use X1 and X2. No, why wouldn't you use, I just gave you X3, X4, X5, I gave you all the observations. So use that information as well in order to estimate the state, right? It depends on what data you are given.
Okay,
right?
clear.
So, and there are situations, I mean, we are in signal processing, we're used to just filtering. We're used to just, let's say, making inferences about states based on everything we've seen in the past. But very often you propose a model and somebody gives you a data set. And you still, if it's a dynamic model, then in that model you have Z1 and Z2 and Z3 and so forth. And really then there is no reason to not use the full data set, right? So then smoothing may be useful. Yeah, I'm waiting for another question. Okay, I don't see a question, so that's good. So next time, Friday, the day after tomorrow, is going to be the last real lecture in terms of new material. We're going to make a step towards intelligent agents. An agent is a machine learning system that can also make actions onto the world. And by making actions, like I can move my head, I can change actually the data that I receive, right? Let's say the data that falls on my retina, I change it by moving my head, right? So, and this is interesting. So now we don't have just a data set and we need to learn parameters, but we can actually influence the data set. And that's more like how we are, right? We are agents. We make actions, we influence the data set, and we also learn from them. And so the question then is, how should we make actions, right? In order to fulfill a certain purpose for us to stay alive, but may be other purposes. So that's what we do next week, and that basically covers the whole class. And then we have another probabilistic programming session and a sort of a fun lecture on what is live, because once we go to agents, it's just a small step to kind of relate that to well, us as Bayesian agents, if you will. Okay, so I will stop the session then, and yeah, wish you good luck in preparing for Friday's class, and I'll see you then. Bye-bye.